Okay, let's get started. Thanks everyone for coming. It's a pleasure today to welcome Professor Nicole Benedek for her inaugural visit to Caltech, hopefully one of many to come. Nicole is someone who works at the interface between condensed matter physics, material science, and chemistry. And today she'll tell you a little bit about the theory and computational methods her group is using to understand complex quantum materials both in and out of equilibrium. So Nicole got her PhD from RMIT, the Royal Melbourne Institute of Technology, in both chemistry and applied physics. I'll ask you later how one does that. Where she worked, where she used computational methods to understand bonding in mixed organic and inorganic crystals. Following her PhD, she, during her postdoc tenure, she split her time between Imperial College London, as well as Cornell University, where she worked on developing computational methods to understand and predict the atomic structure at interfaces between different oxide materials, as well as the response of so-called multiferroic oxides to predict how magnetization could be induced by applied electric fields. Following a short time at the University of Texas, Austin, Nicole then moved to Cornell, where she is now assistant professor in material science and engineering, where she has been since 2015. Nicole has been recognized by multiple awards for her contributions to the area, most recently including the NSF Career Award. So it's a pleasure to welcome Nicole to Caltech, and we're looking forward to hearing about your work.
Thank you for the very kind introduction and for the invitation to speak. As Dave said, this is my first time at Caltech. I've had a really great day. It's really nice to see Cornell alumni, former students who are doing really well. I'd like to tell you about complex materials today. We work on a few different things in my group, but the theme that connects all of the things that we work on is complex materials. So first things first, what do I mean when I say complex materials? I'm going to show you what I mean using the example of the perovskite manganites, one of the classic families of complex materials. So this family of materials have this crystal structure. You are going to be seeing this a lot throughout my talk. The manganese ions are in the green polyhedra, and the atomic sites that are represented by those blue spheres are either a rare earth cation or an alkaline earth cation. So for praseodymium calcium manganite, those blue spheres are either a praseodymium cation or a calcium cation. We care about these materials because they exhibit the phenomenon of colossal magnetoresistance. So their electrical resistivities change by orders of magnitude upon application of a magnetic field. So these data are for praseodymium calcium manganite, and each data set is showing how the resistivity is changing as a function of temperature and applied magnetic fields. Complex materials usually have ground states that are close to multiple phase boundaries. So when the calcium content is 0.3, then depending on the temperature, the material is close to a charge-ordered insulating phase. So this is ordering between manganese 3 and manganese 4+, a paramagnetic insulating phase, a ferromagnetic insulating phase, an antiferromagnetic insulating phase, and so on. So in these kinds of systems, changing the calcium content not only changes the whole concentration through the manganese 4+ concentration, it also subtly changes the crystal structure, which in turn changes the spin order and the orbital order. Because complex materials are close to multiple phase boundaries, their properties tend to be highly tunable or highly controllable with external handles, like epitaxial strain, pressure, or chemical substitution. So for this system, praseodymium calcium manganite, the change in resistivity with field can be tuned with pressure and also with chemical substitution onto the A site. Right, so putting all of those things together, complex materials are typically characterized by many competing degrees of freedom, ground states that are close to multiple phase boundaries, and properties that are highly tunable with external handles. All of that also gives rise to the possibility for cross-coupled responses, where the electric fields can be used to control the spin degrees of freedom, and magnetic fields can be used to control the charge degrees of freedom. These systems are usually scientifically very interesting. They usually teach us a lot about fundamental condensed matter science. And they also often have the potential to be technologically useful. Right, so how do we create or find complex materials? How can we leverage their properties in useful ways? So almost everything that we do in my group is geared towards answering these kinds of questions. We are a theory group. We use a combination of theory, phenomenology, and first principles, DFT calculations to explore these questions. And you'll be seeing all of those approaches in action throughout my talk. And so in the first part of my talk, I'm going to tell you about some work I did on discovering mechanisms that exhibit a cross-coupled response to electric and magnetic fields. So these materials are polar. They have globally broken inversion symmetry, and they're also magnetic. And the magnetic moments couple directly with electric fields through the lattice. So as Dave mentioned, this word multiferroics, these materials are known as multiferroics. They are of interest for, to give one example, ultra low power computing applications. I'm not really going to get into any of that today. The point of the first part of my talk is really to demonstrate an approach to thinking about problems or understanding problems. And then in the second part of my talk, I want to show you how you can use that same approach in a different context, one where light is the external handle, so using light to change the properties of materials. Just a heads up about some terminology that I will be using. I will use the word ferroelectric to refer to a material that is polar, so it has a spontaneous macroscopic polarization, the direction of which could be switched with an applied electric field in principle. So I'm basically going to use the words polar and ferroelectric interchangeably. It's just a quirk of this field that we're a little bit sloppy with language. All right. So the family of materials that we spend most of our time working on are the perovskites. This is known as the cubic perovskite structure, and it's often taken as the prototype for this family of materials. So perovskites have a cation on the A site, a different cation, typically a transition metal on the B site, and that's octahedrally coordinated by anions, usually oxygen. Perovskites are awesome because this one structure type can accommodate nearly every element of the periodic table. And that chemical versatility leads to a huge range of different properties. That list up there is not exhaustive. The other reason that perovskites exhibit so many different properties is that despite this being known as the prototypical cubic perovskite structure, most perovskites don't actually have that structure in their ground states because they undergo some form of structural distortion or structural phase transition. And so the tolerance factor is just a very simple empirical measure that relates the stability of a perovskite in the cubic phase to its chemical composition. So up here, RAO and RBO are the ideal AO and BO bond lengths. When T equals 1, that indicates perfect close packing. And so the material is predicted to be stable in this cubic structure. When T is less than 1, that means that the A site cation is underbonded in the cubic phase. So the bonds that the A site cation makes to the surrounding oxygen ions are too long. And the material is predicted to undergo a so-called octahedral rotation and tilt distortion, which shortens the length of those AO bonds. So these are the two most common space groups that are adopted by perovskites that undergo rotation distortions. They tend not to be polar, and I'll be saying more about them in a little bit. When T is greater than 1, that indicates that the B site is underbonded in the cubic phase, and a polar or ferroelectric distortion is predicted to occur. We care about these structural distortions because they have a huge effect on the electronic and magnetic properties of perovskites. And indeed, we can exploit these distortions to create functional materials. So octahedral rotations and tilts really mediate the electronic and magnetic properties of perovskites. So the rare earth nicolates undergo both metal insulator and magnetic ordering transitions. They vary from being paramagnetic metals to antiferromagnetic insulators to paramagnetic insulators as a function of tolerance factor. Right? So as the tolerance factor is decreasing here, these rotation distortions are getting bigger and bigger. And so it's basically tracking this metal-oxygen metal bond angle, which is getting more and more bent away from 180 degrees. And you can see similar things in the manganites that I just mentioned. The problem is that most correlated perovskites, so perovskites with interesting magnetic and electronic properties, are not polar. So it's not clear how we might access all these wonderful properties in a practical way. And by practical, I mean ideally electric field control. In fact, over half of perovskites, that's this big slice of the pie here, adopt this orthorhombic PNMA crystal structure and are not polar. Right? So if we really want to achieve this goal of creating these cross-coupled complex materials, then one way forward might be to start with a magnetic perovskite and then look for new mechanisms of inversion symmetry breaking. So how is inversion symmetry broken then just in prototypical perovskite ferroelectrics? So in polar and ferroelectric materials, there is a spontaneous macroscopic polarization. The polarization arising from a row of alternating, equally spaced positive and negative ions is 0. In materials with polar ground states, there's an instability such that when the ions are displaced from their symmetric positions, a polarization arises and the energy of the system goes down. Right, so if we look at lead titanate, in the structure on the left, it's cubic, all the ions are sitting on high symmetry sites, the polarization is 0 by symmetry. In the structure on the right, the titanium ion has moved up a bit. That breaks inversion symmetry and allows a polarization to arise. The polar lattice distortion is a vector, let's call it U. It has symmetry properties that are identical to the polarization, so it transforms like a polar vector. And in these D0 titanate perovskites, ferroelectricity is induced by cross-gap hybridization between the titanium 3D states, which are formally empty, and the oxygen 2p states that sit at the top of the valence band. And so the instability that gives rise to the polarization is associated with an unstable IR active phonon of the high symmetry phase. So what do I mean by an unstable phonon? So we look at a toy model of a stable phonon. We have a ball sitting in a potential well, and it's oscillating back and forth about its equilibrium position. And the frequency of the oscillation is just proportional to the curvature around this point. And so if I calculate the frequency squared here, I'll find that it's positive. Okay, so displacing ions along this coordinate raises the energy. If, on the other hand, the underlying potential at t equals 0 looks like this, so I can put my material into the structure that corresponds to this saddle point. That's the high symmetry phase. And if I calculate the frequency squared around this point, I'll find that it's negative, indicating that the material is unstable towards this particular structural distortion. It doesn't want to be up here, it wants to be down here. So this is known as the soft mode picture or the soft mode mechanism of ferroelectricity. And over the years, people have come up with a number of different strategies for inducing polar ground states in nominally non-polar materials based on this mechanism. The problem is that those strategies are not really amenable to producing the kind of cross-coupled complex materials that we're after. And so can we find another way? And just a teaser, the answer to that question is going to be a novel form of inversion symmetry breaking in layered perovskites. So this is known as a Ruddlesden Popper phase. It was a theoretical prediction first, and then it was verified by experiments a few years later. So these images show some of the very rich and beautiful domain structures in this system, and some equally beautiful polarization hysteresis loops. So the polarization here is actually switchable. But before we get to that, we had to answer this question. So why is it that the majority of perovskites are not polar? Right, so say you have some system and you're interested in understanding, why does this system have the properties that it has? Or why doesn't it behave in some other way? What can you do? Well, we have very sophisticated experimental, theoretical, and computational techniques these days. You can do various physical properties measurements. You can develop very sophisticated theories. You can calculate properties to higher accuracy than ever before. You can synthesize either in the lab or in the computer a whole series of materials that change as a function of, say, composition, and see how the properties change. You can do all of those things, and they're not bad things to do. They're perfectly good things to do. But you can also do something else, which might seem a little counterintuitive at first. You can restore symmetries that are broken. So we're looking for ways to break symmetry, and one way to learn how to do that is to restore symmetries that are broken. So there are formal, systematic group theoretical and representation theory ways that you can use to do this in a systematic way, and that's what we do. But I'm going to explain this in a conceptual way to give you the big picture. If you would like the details, or if you would like to learn how to do this for yourself, there's some excellent starting references down there. Right, so if we look at this structure, the broken symmetry structure, we just look at that for a minute, what do we see? Okay, so we see those polyhedra that are connected to each other. And we can see that they're kind of tilted and rotated with respect to each other. And so one thing that we could do is untilt them or unrotate them so that everything is all nicely lined up, all those polyhedra. And that will restore some symmetries and take me to some higher symmetry space group. Another thing that I can do, it's hard to see from this image, but these A-site cations are offset from each other in the layers. So I can make it so that they're all nicely lined up, and that will restore some symmetries and take me to some higher symmetry space group. And then I can keep doing this until I can't get any higher in symmetry. And then I eventually end up with this high symmetry paraphase. This low symmetry structure is in a subgroup of the space group of this high symmetry paraphase. Right, so that high symmetry paraphase might be an actual high temperature structure in the phase diagram of your material, or it could just be a virtual reference structure. The distinction is not important for our purposes. The structural distortions that relate these two structures are known as modes. So they transform like irreducible representations of the point group of the high symmetry paraphase. And we can treat those modes kind of like order parameters in a Landau theory. So we can expand the energy about this high symmetry paraphase in powers of these modes. And doing that, seeing how different modes are coupled together, what the couplings are, gives us a lot of information about the mechanisms through which various symmetries are broken. Right. So let's do this now for this structure. So if we start from the high symmetry paraphase, and then we can add in these two different distortions. These are their IREF labels. We don't have to worry about them. And if we superimpose these two modes, then we get this orthorhombic PNMA structure. Right? So all you need to establish the PNMA space group symmetry is these two modes. That's all you need. But that doesn't mean that other kinds of modes aren't allowed by symmetry. And if you look at all of the modes that are allowed by symmetry, then you will find this one that involves displacements, these kind of antipolar displacements of the A-site cations. And there is a trilinear term in the energy that couples all of these distortions together. Okay, so that means in the ground state, in this PNMA ground state, we can't control the amplitudes of those modes independently. They're all coupled together and they all affect each other. Right? So these A-site cation displacements induce a polarization, these little local dipoles in the AO layers. Right? But because the A sites are related by inversion symmetry through the B site, the polarizations that are induced are exactly equal and opposite and cancel out. So the macroscopic polarization is 0. In fact, you can show that these A site cation displacements globally suppress distortions that globally break inversion symmetry, even though they induce a polarization, these little local polarizations in the AO layers. And the material up here is not important. It's strontium stannate, but it's not important. And so one of the most straightforward things that we can do is to make a layered system and simply replace every other layer of AO cations with a different cation. So here, instead of having all layers of SRO, we can just replace every other layer with barium. And now, because strontium and barium are different sizes, they displace by different amounts, and the polarization does not exactly cancel out. So you have a macroscopic polarization. If the cation on the B site is magnetic, then the polarization and the magnetization become coupled up through the lattice. Right? And again, there's a trilinear term in the energy expansion that couples together the polarization and these two rotation distortions, R and M. Okay, and because of this, the trilinear kind of nature of this term, if one of these modes changes sign, so say if the polarization changes sign because we put on an applied electric field, then either one, but not both, of these distortions also has to change. Okay, so this form of inversion symmetry breaking is very different to that soft mode picture that I started my talk with, because instead of having one mode, there's two nonpolar modes. So they're nonpolar individually, and then they combine to induce a polarization and to induce a polar ground state. And then because of the form of this trilinear term and the fact that these things are coupled to other properties, like weak ferromagnetism for one of the rotation distortions here, then that enables exactly the kind of cross-coupling that we're after. Right. So there has been sort of a ton of work in this field and on this mechanism since I started working in this area that I don't have time to talk about, but my long-term collaborator, Mike Hayward, and we wrote a review last year that kind of summarizes the state of the art up to this point, experiments and theory. And so if you would like more details, there's a lot more in that paper. And so what I'd like to show you now is how we can use this approach or this way of thinking about complex materials to enable control of properties now where light is the external handle. So specifically how we can use light to control magnetism or switch off bulk magnetism in perovskite gadolinium titanate. This is a D1 titanate. It's ferromagnetic in its ground state. So there's a specific kind of experiment that I'm thinking of here. So let me start this section by saying a few words about that. So here's an example of such an experiment on a material that I started my talk with, praseodymium calcium manganite, and it's a very complicated phase diagram again. So what was done in this experiment was that a laser was tuned to the frequency of one of the IR active phonon modes in the material. It's one that involved displacements of these manganese ions opposite these oxygen atoms. Oops. And what these authors see after exciting this mode is a change in the reflectivity of the material that's consistent with an insulator to metal transition. And so if I just go back quickly to this phase diagram, the material is insulating over this whole section of the phase diagram. So this goes up to 400 Kelvin, and the experiment was done at 30 Kelvin, I think. And that metallic state persists for quite some time after the initial light pulse. By varying the wavelength of that optical excitation, they see the maximum change in conductivity occurs at the energy of that 71 millieV phonon mode. Okay, so the interpretation of what's going on here is that these changes in properties are due directly to movements of the atoms, displacements of the atoms that are induced by optical excitation of these modes, because electronic excitations are gapped at these frequencies. Okay, so this is a cartoon, and I want to emphasize that this is very cartoonish of the basic physical process or mechanism that was proposed to explain the results of the experiment that we just saw. So it's been dubbed the nonlinear phononics mechanism. Like I said, a laser is tuned to resonantly excite one of the IR modes in the material of interest. That material, or that mode, sorry, then starts ringing because we've just dumped a whole lot of energy into it from the light pulse. And then in some materials, there is a coupling between the modes, which looks like this. Other kinds of couplings are definitely allowed. This one, I think, has just been the most well explored in the literature. So a coupling between the IR mode and other modes, Raman active modes, such that as the IR mode is ringing, it pushes on these other phonon modes it's coupled to, and they also displace. And in a real material, the vibrations don't go on forever. Of course, the energy that we put in the form of the light pulse has to go somewhere. So we're interested in the transient response before thermalization. So the first challenge that we really had in trying to do work in this area was, how do we get the information that we need? What information do we even need in the framework of first principles theories? And so I wanted to spend just a couple minutes telling you about the model that we formulated to do this work. Right, so we consider only the instantaneous response of the lattice to the light pulse. Right? So we assume that the light pulse has gone past, and the only energy that's left is mechanical energy, so to speak. So we don't include coupling to Maxwell's equations. This is the imaginary part of the dielectric function for gadolinium titanate for light that is polarized along a particular crystallographic axis. So these peaks are all the IR active modes that are polarized along this direction. This gray shape is the power spectral density of the light pulse, and it's peaked at the frequency of one of those IR active modes. We generally assume a Gaussian pulse with a 300-ish femtosecond width. The allowed modes are determined by the incident light polarization. And of the allowed modes, we include all symmetry allowed phonons and not just the optically excited one. So the optically excited mode transforms like some irreducible representation of the point group, and everything else that transforms in that same way is going to get displaced when an optical pulse comes in. And so we account for all of that. The oscillator strengths just come from first principles. And then this broadening here is just a fit to get good agreement with experiments. We don't use that information for anything else, although we are now calculating it explicitly, and it's a fair amount more work. Right, so in the first part of my talk, I was telling you about how you have some high symmetry paraphase, and then you can expand about that paraphase. So exactly the same idea here. We're treating the crystal before optical excitation as the high symmetry paraphase, and then expanding around that. So here the omegas are the phonon frequencies, and the Qs are the amplitudes. And then there is the coupling term to lowest order. The coefficient A tells you how strongly those two modes are coupled together, and its value is material dependent. And then the very last term is the polarization change in the crystal due to the electric field of the incoming light pulse. So there are both lattice and electronic contributions to the polarization. So here, Z star tilde is the dynamical mode effective charge of the IR mode. It tells you how strongly the IR mode couples to the incoming light pulse. Changes to the changes in the polarization due to the coupling between the IR and Raman modes can have a very significant effect on optical properties. So there's lots more about that in this paper, although for the work that I'm going to talk about, we just cut the polarization off at linear order. And then from that expansion, we can get some equations of motion that tell us how the amplitudes of the various modes change in time in response to optical excitation. And then these are the solutions to those equations of motion. So this top panel is the IR modes, showing how their amplitudes change as a function of time. So this one here that's changing a lot is the one that's actually excited, and everything else gets a little wiggle as the light pulse moves past, but then doesn't change very much. And then the Raman modes are down here. Their amplitudes can increase or decrease with respect to equilibrium. Okay, so we take these amplitudes and then we can add them back to our equilibrium crystal structure and see what effect that has on the properties that we're interested in using first principles calculations. So basically what we have is a phenomenological model. The input to that model comes from first principles calculations, and then the output gets fed back in to first principles calculations. All right, so what can we do with that technical machinery? So the first thing that we worked on was this family of rare earth perovskite titanates. So here is that PNMA crystal structure again, with octahedral rotations, and the magnetic properties of these systems change as a function of the magnitude of that distortion. So for smaller octahedral rotations, larger rare earth cations, the spins on the titanium ions align in this G-type AFM configuration. For smaller rare earth cations and larger octahedral rotation distortions, the spins align ferromagnetically. This dotted line means that there's no stoichiometric material that exists in there. But if it did, these guys, Mochizuki and Amada and others pointed out, if you could have a material in there, then it should have this A-type AFM configuration. Now, it might seem as if the magnetic properties are very dependent on this rotation distortion. And so you should be able to realize this A-type AFM state by judiciously tuning those rotation angles using pressure or strain or substitution or something like that. But that's not so easy to do, because this A-type AFM phase requires the combination of a strong Jahn-Teller distortion, so that's a distortion of the oxygen environment around the titaniums, and a moderate octahedral rotation distortion like in samarium titanate. The problem is that those modes are anharmonically coupled together. So again, if you look at the expansion, the free energy expansion about the paraphase, you'll see a term that couples these modes together. And the A-type AFM phase depends on them going in opposite directions. So in other words, if I try to make the Jahn-Teller distortion strong, like in gadolinium titanate, then I also make the rotations bigger, and that's bad for the A-type AFM phase. And if I make the Jahn-Teller distortion, or if I make the rotations weaker, like in samarium titanate, then the Jahn-Teller distortion gets weaker, and that's also bad for that A-type AFM phase. Right? So there's no known way to independently control the relative magnitudes of these distortions. And so our idea was, well, can we take gadolinium titanate, which sits on the phase boundary there. It's a ferromagnet at equilibrium. And can we tip it over into the A-type AFM phase with light? So can we switch off the bulk magnetism with light? So what this plot is showing is the difference in energy between the A-type AFM phase and the ferromagnetic ground state for excitation of a 70 millieV-ish phonon mode polarized along this long axis. Positive energies mean that the ferromagnetic ground state is more stable than the A-type AFM phase. And so as the peak electric field of the light pulse increases, the energy of the A-type AFM phase decreases relative to the ferromagnetic ground state, but the system remains ferromagnetic over this entire range of peak fields. And yes, we could have just kept going, but ideally you want the peak fields to be as low as possible. So we needed some way to position the system closer to that A-type AFM phase boundary. And so we thought, well, let's try epitaxial strain. So this is a very similar plot showing the difference in energy between the ferromagnetic ground state and various AFM orders as a function of biaxial epitaxial strain. So we're applying the strain in this plane perpendicular to this long axis. So the A-type AFM phase is the black data points, and they're closest in energy to the ferromagnetic ground state. And the AFM A phase becomes the lowest in energy at both large tensile and large compressive strains. So in principle, maybe you could realize this magnetic phase using strain alone, but those are pretty large, ungodly strains. But if we back off a bit to 1.5% tensile epitaxial strain, that's a little more reasonable. The system is perched right on the edge of the phase boundary with the A-type AFM phase. And so now maybe we just need to give it a little tip over with light. Okay, so this is the same plot that I've shown for the past couple slides, but this time for its excitation of the same phonon mode, but for 1.5% tensile strained gadolinium titanate. And now we see this crossover from the ferromagnetic phase to the A-type AFM phase at much lower peak electric field values. Right, so this A-type AFM phase is hidden. It doesn't exist in the equilibrium phase diagram of any of the rare earth perovskite titanates, but maybe it is dynamically accessible in strained gadolinium titanate. So the next question was, well, we know that atoms are getting displaced, modes are getting displaced. So how does optical excitation change the crystal structure to facilitate this change in magnetic order? So can we trace this back to a particular distortion? Right, so we usually think of the electronic and magnetic properties of perovskites as being controlled by these octahedral rotations and tilts, as I've mentioned several times now. So let's look at them first. So this is a schematic phase diagram showing the change in the spin order as a function of the magnitude of one of those two main distortions in gadolinium titanate. So remember I said there's two rotations that together establish the PNMA space group symmetry. This is one of them. And so here are the rotation angles that are up here. Right, so small rotation angles correspond to the G-type AFM phase, and larger ones to the ferromagnetic state. Right, so this change in magnetic order is usually understood as a response to changes in the titanium-oxygen-titanium bond angles, which are strongly modulated by this distortion. But if you try to interpret our results in terms of this picture, then you find something unexpected. Right? So if we look at our strain results again, and just focusing on small strains plus or minus 1% of the bulk value, that's going to be most relevant to experiments. So tensile strain is this way. That's favoring the A-type AFM phase. And compressive strain is this way. And that's favoring the ferromagnetic ground state, further stabilizing that ground state. Okay, so how does this compare with what we see in bulk? All right, so this is the same phase diagram that we were just looking at. And this highlighted red region shows the range of rotation angles from our strain calculations. So this rightmost edge is the largest tensile strains, and this leftmost edge is the compressive strains. And so what this is saying is that under tensile strain, the rotation angles are changing in such a way that we would expect the ferromagnetic ground state to be further stabilized. And under compressive strain, the rotation angles are changing such that we would expect the A-type AFM phase to be stabilized. Okay? But that's the exact opposite of what we actually see, which is that tensile strain is favoring the A-type AFM phase, and compressive strain is favoring the ferromagnetic phase. Then we look at what happens under optical excitation. So that's this highlighted blue region. And the rightmost edge is the largest peak electric field that we tried. And so we look at how the structure is changing. And the structure is changing such that we would expect that as the peak electric field increases, the system should go further into the ferromagnetic part of the phase diagram. And again, that is exactly opposite to what we actually see, which is that as the peak electric field increases, we should go further into the A-type AFM part of the phase diagram. This is the other main rotation distortion that makes up the ground state structure. So this time, neither strain nor optical excitation gets you into the right part of the phase diagram, right? And the change in rotation angle here is just so wimpy, like half a degree. Right? So the point that I'm trying to make is that if you are trying to explain the change in magnetic order using these changes in the rotation angles, you just can't do it, right? Because the kind of theory that you get from this rotations control the magnetic strain just does not match what we actually see. Right? So if it's not the rotations, then what is it? So I mentioned that in this PNMA space group, you have those two rotations. Those are the large amplitude distortions. But there are a number of other distortions that are allowed by symmetry. So there's 5 in total. Here are those antipolar A-site cation displacements that we saw earlier. And then what I'm showing in the middle is that we decomposed the dynamical response of the crystal, so how the crystal structure changed in response to optical excitation into contributions from all these different modes. Okay, and these numbers, this is a percentage, so these numbers add up to 100%. Right, so here are the two rotations that should be running the show. Like, yeah, their amplitudes change, but not very much. The distortion that makes the largest contribution is this Yarn-Teller distortion. So it has a very tiny amplitude in the equilibrium structure, but it changes by a lot under optical excitation. Okay, so the same kind of plot that we saw before, except here I've separated out these curves into different contributions. So this top one up here is where only the rotation distortions were allowed in the dynamical response, and everything else was put back to the values that they have in the equilibrium crystal structure. Right? So now the crossover between the magnetic phases happens at super, super high peak electric field values. It's only when you allow these other very small distortions that are coupled to the rotations that you can recover that crossover at moderate peak electric fields. Right? So when you're working on these systems, yes, the rotations are important, but there are a lot of other distortions in there that are much more subtle. And time again in my work on these systems, I've been working on them for a long time now, these small subtle distortions turn out to be decisive for the physics. I mean, you can't even qualitatively explain what's going on if you don't take account of them. So we've done, this is a very complicated picture, but we've done a ton of other work and working on stuff now. So basically mapping out the phase diagram for this nonlinear phononics mechanism. There's a lot of other kinds of couplings that are allowed. So, you know, what I've presented today is kind of this corner, but there's a lot of other stuff to be explored. And so that's what we've been doing, using a combination of flow K theory and first principles calculations. We will be at APS very conveniently in the same session, S38 on Thursday morning. That reminds me, I have to register. So if you want to learn more about that stuff, then please.
I have learned that 90 ounces is.
I think I've been talking for long enough. Really, the take-home message is that small, even tiny structural distortions in complex materials can really matter a lot, and that the crystal structure is as important as the electronic structure. That will be carved into my gravestone. I want to acknowledge my wonderful students and postdocs who work so hard. This was their work that I presented, and the people who gave us money, and all of you for your attention.
Okay, questions for Nicole? Brent and then Patrick.
Yeah, very interesting. I'm wondering if you have any comments about the connection of these flows, which are allowing these distortions to occur, to the thermodynamic free energy. Is there anything useful there? There was a whole Cambridge group that was trying to do these rigid unit flows.
Yes.
You're not committing their sins, but you might have seen some of what they're trying to do.
So I know exactly what you're talking about. And in the work that we did, not this work, but on thermal expansion in lead titanate, that is a system that has many of these, rigid unit modes. And what we found is that they were completely unimportant to the thermal expansion. I mean, they're there, but they're not really important.
Yeah, they're not rigid either.
And they're not rigid. No.
Yeah, I'm confused with it. I think when you drive a system, you generate a linear term with QR, right? The linear. It is Q squared times QR. So you generate a term that's linear.
Yeah.
So that would display the parabola, but the picture you draw has a double minimum. So that means a negative Q squared. So I got confused.
I think two completely separate things.
Oh.
So yeah, I mean, that is the coefficient of the QR term in this case will be negative. So I drew this when I was talking about the kind of the soft mode picture of. Yes, yes.
But the mechanism that you are describing is a linear.
Yeah, it's different,
Okay,
totally,
so
totally
different picture.
not connected. Yes, yeah, different thing. Yeah.
And I think in the early slide you showed that this thing lives for 500 picoseconds. Is that
Yep.
theory or experiment?
That's experiment. That was all, I don't have my cursor. That was, yep, that's an experiment.
Why would
This is what I was talking about with Eugene and with you. I was hoping that you we're all curious, but we had a long discussion with Eugene, and so maybe there's a metastable state in on the energy surface that it gets trapped in.
that's not true? I think you expect picoseconds.
Yeah, exactly. No, I agree with you. Like it's not.
So is this seen? Which system is it seen?
That was praseodymium calcium manganite.
Is it seen anywhere else?
I believe on the experiments, some of the recent experiments on strontium titanate, pumping the polar mode in strontium titanate. I don't remember the exact time, but it's also very long. It's not like picoseconds. So yes, it is seen elsewhere.
Just following up, to what extent can your DFT calculations capture these
The
metastable
life,
states?
but you mean their lifetimes?
Still presence.
It's not an issue. I mean, so we captured that A-type AFM phase. Like if you can just put the modes in there, and you have that metastable state, and in our calculations it lives forever. There's no damping. What I'm trying to figure out is how to get the lifetime, like what determines the lifetime. And it's not just a simple the lifetime of the IR mode, because there's orders of magnitude difference between that and what is actually seen.
In these gadolinium titanates works, there's also a moment on the A side.
Yes.
Does that do you ignore those? If not, do they play a role?
So we ignore those. So the rare earth moments order at much lower temperatures than the titanium moments. So we've not taken account of them.
Any other questions for Nicole? Brett?
Yeah. These distortions have some sort of some range, some restoring potential. How do I look at this? It's not a harmonic one. It's probably a higher power. Do you have any units like it's working for that?
Which kinds of distortions?
Any of these that are kind of approaching an instability, but not there yet. The type of restoring force for the distortion parameter is going to be some power of the distortion somewhere, I suppose.
Yeah.
Opinion on what it is?
So at the instant of optical excitation, the restoring force of the harmonic term will be negative. And then for the higher order terms, I mean, I don't know what the relative ratios of the coefficients are, or it would be straightforward to get, but we haven't looked at it.
Changes the excitation. So
It's relatively straightforward. We just haven't done it.
Okay, well, if there's nothing else, let's thank Nicole again for a great talk.